You've heard the term the world's safest train. It's a title earned over decades. A reputation built on zero fatalities, millions of miles logged, and engineering so brilliant it seemed foolproof. But safest doesn't mean invincible. It just means failure is incredibly rare, until one day it wasn't. This is the story of how a system designed for perfection suddenly, catastrophically failed. To understand what went wrong, we first need to appreciate what made this train so safe. It was a marvel of modern engineering. The system was packed with redundant sensors, designed so that if one failed, another would instantly take over. It featured a sophisticated automatic braking system that could react faster than any human. Maintenance schedules were brutally strict, with every component checked and rechecked long before it was expected to wear out. The train was a fortress of safety, optimized to handle every imaginable problem, but its greatest strength was also its greatest weakness. It was designed for known scenarios, and on that fateful day, it encountered something it had never been taught to see. It all started with a tiny, almost imperceptible anomaly. It could have been a sensor drifting out of calibration by a fraction of a degree. Maybe it was a single line of corrupted code in a software update, or perhaps just a thin layer of ice or debris on the track that the primary sensors did unregistered correctly. To the train's central computer, this anomaly didn't look like a threat. In fact, it looked perfectly normal. Why? Because of a hidden flaw in its redundant design. The backup systems, the very things meant to prevent disaster, were all designed in the same way. This is called correlated redundancy. So, when the first sensor was fooled by the strange input, the second and third sensors were fooled in the exact same way. They all reported the same incorrect information. The computer, seeing three identical signals, did exactly what it was programmed to do. It trusted the bad data. The failsafe had become a faildane. A system designed to have no single point of failure had just found one. Compounding this was a subtle flaw in the software logic. The thresholds for what constituted an emergency were programmed to be slightly forgiving to prevent unnecessary jarring emergency stops during normal operation. A rate limiter, designed to smooth out the train's reactions, ended up delaying the emergency brake command by just a few critical seconds. At the same time, you have the human element. The crew, working in the cabin, had grown to trust the automated system completely. Why wouldn't they? It had never failed before. They'd seen countless minor alerts that the system always handled on its own, leading to a phenomenon known as alert fatigue. When the critical warning finally flashed, it was just one more notification in a sea of routine alerts. Their manual override came, but it came too late. Then there's the reality of maintenance versus the theory. On paper, every part was serviced perfectly. But in the real world, components don't always fail in a predictable way. Microfractures in a connector, slight wear on a cable, or a tiny calibration error can introduce silent, invisible errors into the system. These aren't the kinds of things that show up on a standard diagnostic check. They just sit there, a ticking time bomb waiting for the right conditions to detonate, and those conditions were about to arrive. Another huge risk was hiding in plain sight: system integration. The train systems weren't built by a single company. The brakes were from one vendor, the sensors from another, and the control software from a third. Each component was updated on its own schedule. A recent software patch for the signaling system had slightly changed the timing of data transmission. It was a minuscule change, but it was enough to disrupt the delicate dance between the train's brain and its brakes. A system of perfectly engineered parts became a dangerously uncoordinated whole. All these hidden problems were about to collide. A minor operational delay earlier in the day had caused a domino effect. To make up Chimmy, the network controllers had compressed the headways, meaning the distance between trains was shorter than usual. This left almost no margin for error. The system was now primed for failure. As if on cue, the environment decided to play its part. A sudden downpour made the track slick with rain and leaf mulch, a condition notorious for causing adhesion loss, or simply slip. The train's ability to brake was suddenly and drastically reduced. This was the moment of failure. The train's computer, fed a stream of bad data, believed it was traveling at a safe speed with plenty of room to stop. But in reality, thanks to the slippery tracks, its braking distance had more than doubled. The gap between what the train asterisk thought asterisk was happening and what was asterisk actually asterisk happening widened with every passing second. The point of no return was crossed. The crew, finally realizing the automation had failed, slammed the manual emergency brake. The sanders, which dropped sand on the track to increase friction, were deployed. Desperate calls were made over the radio, but it was a race against physics they were destined to lose. In the aftermath, the investigation began. The train's black box, its data recorder, told the whole story with cold, hard facts. It laid out the precise chain of events. The initial sensor anomaly, the computer's misclassification of the event, the delayed brake command, and the final, futile manual intervention. The root causes were a textbook example of coupled failures. It wasn't just one thing. It was a technical failure of sensors and software, a human failure of overtrust and complacency, and an organizational failure of maintenance and integration, all happening at the worst possible moment. The incident forced a complete overhaul of the system's safety philosophy. The fixes were immediate and for reach. The old correlated redundant sensors were replaced with a system of uncorrelated redundancies in different types of sensors, like radar and LiDAR running on different algorithms. This way, if one type of sensor was fooled, the others wouldn't be. The software logic was rewritten with stricter thresholds and a much faster trigger for the emergency brakes. New health monitoring systems were installed to constantly check for sensor drift and perform self-tests, catching those silent errors before they could cause harm. Most importantly, crew training was completely revamped, focusing on graceful degradation, teaching pilots to recognize the subtle signs of automation failing and to intervene early and decisively. Regulators stepped in, mandating that all new systems undergo rigorous edge case drills, simulating the exact kind of bizarre, unpredictable scenarios that led to this disaster. They also enforced synchronized update schedules for all vendors, ensuring that one company's patch wouldn't inadvertently break another company's component. The biggest lesson learned wasn't about a specific sensor or a line of code. It was a fundamental shift in understanding what safety really means. Safety isn't a trophy you win and put on a shelf. It's a continuous, dynamic process. It requires assuming that failure is always possible and designing systems not just for what usually happens, but for the 1 in a million what if. The safest systems in the world don't stay that way by celebrating their past successes. They stay safe by relentlessly studying their near misses and learning from their failures before they become headlines. Thanks for watching. If you found this breakdown interesting, consider liking this video and subscribing for more deep dives into the engineering that shapes our world. Stay curious and stay safe.